So here we will continue our discussions on the granular mechanics simulations. So the second part of the talk is motivated by the fact that for many natural material, the particle shape doesn't resemble a spherical particle. In fact, in many cases, it has a very complex geometry for each individual particle. You can see here as an example. In this particular example, you can see multiple local non-convexity, and on top of that, not only is the aspect ratio are actually not 1-to-1, but the local non-convex feature may lead to a contact that are interlocking each other. If you want to simulate the important mechanics of the particle, what we actually could do is to simulating it with the classical contact mechanics finite element. But this approach would actually have a big burden on simulating the complex boundary. Because if you use a mesh-based method to model the particle, we have to able to simulate a lot of the details of the particle with a fine mesh just to capture the geometry. But as you can see here, if the contact of the particle are actually in the area that doesn't necessarily have geometrical complexity, we may actually losing this fine mesh that we call computation time to get a displacement field that doesn't necessarily to have much consequence for the mechanics behavior. Okay. And our goal of actually also generating more realistic simulation is also due to the fact that in the recent year, we have the new technology that allow us a more precise verification program that the 3D printing basically enable us to simulate individual particle and also to print individual particle such that the individual particle can need to assemble of a DEM like particle. But the interesting thing is that in this highly controlled element, we can have different particle shape, and yet each individual particle will virtually have a similar property. So that would allow us to isolate some of the effect and purely study the shape effect on the microscopic outcome when we conduct a different test. Shown here is one simple example where we have the 1D compaction test, and then on the 3D printing material, and we can seeing that very interesting 1D compaction curve, and the compaction curve can be deducted from the 3D print material. So why do we want to simulate the contact in great details? And why do we want to simulate a deformable particle? The reason is actually the following. If you want to understand the details of the contact, and if the contact is actually important for us to understand the granular mechanics, we actually need to not only able to use the DEM to simulate the change of the individual particle topology change inside the entire ensemble, but we also want to simulate different nature of contact that not necessarily can be covered in a simple overlapping mechanism. So here is one example. So you see 4 particles, 1, 2, 3, 4, and they're in contact with each other with a wall that are also deformable. If we simulate it with this discrete element, we may get a shape that somehow looks like this. Okay, and we may actually even get a similar stress strain, except maybe for this point where the non-convexity need to 3 contact points for a 2 particle instead of only 1. Now, what actually happened is that when you actually have a discrete elements, you only saw the displacement of the centroid of the particle. There is no way from this 4 displacement field you can recover the stress. And if we cannot recover the stress, there are consequent and limitations of that numerical simulations. The first one is that obviously we cannot model the fracture behavior properly because if we look at it in small scale, we need the stress concentrations and the energy flux in order to propagate fracture according to the classical fracture mechanics theory. Without the force, with only the displacement and then the force that are caused to contact, there's no way for us to actually predict the fracture, as we mentioned in the previous lecture. You can give one example. If we have a contact that are actually point-wise, if it is a single point, even a force that are very small divided by zero area would lead to a singularity. Okay, there are previous methods that actually simulate a particle with a finite element that allows some deformity. But actually what we want to concentrate here is to actually analyze if you allow the capture of the stress concentrations in great revolutions, what would be the consequence if you also allow the damage of the particle? And how does that damage evolving the topology further and lead to a more complex, small structure revolution that can be captured numerically, and from that, how does it affect our macroscopic simulations? So those are the questions that may bring up from a more detailed simulations, and hence we are willing to pay the price of a much higher computational cost in order to achieve this goal. So here, this is actually the background. We want to deal with the challenge without necessarily using a finite element contact problem. The reason is that imagine that we have 100 or maybe 1,000 of particles, and we actually want to deal with it in finite element, generating right mesh, and then cleaning it up to prepare the mesh for individual particle and create a mass slave pair for the contact mechanics. This is simply not attackable, checkable, or doable task. And then on the other hand, the alternative we have is a DEM that both are based on simplified shapes per pseudo-statistic. And then also we have to deal with the loss of the detail on the contact, because in the DEM, either you can actually assume rigid body, no penetrations, but then the force, but then the stress, you would actually also lose the stress, or we can actually allow the overlap, which could actually also damage the details of the granular contact, particularly if you have more than one contact point between the particle. So the key point is the following. How do we actually get the benefit of both to some extent and come up with a new numerical method that are easy to use and yet doesn't necessarily not compete, that being so computational expensive that are not usable? So what we actually did is that we would use a voxel-mesh. Now, based on the previous work that we actually use and actually extend it to the frictional contact algorithm. Okay. So now, in this approach, we will represent individual particles as a level set, but we will have a fixed background mesh. Okay, so the particle locations are actually represented by the indicator functions f and g, for example, in these two problems, or maybe f1 and f2. And if f1 equals to 1, we know this is the boundary. If this is positive, we know it's outside. If it's negative, we know this is actually inside the individual particle. Now, with the mesh, the advantage of this is that we don't necessarily need to mesh the element, because if we have a level set to indicate the locations, we can simply, using the indicator functions that are stored in the entire grid as a scalar value to tell us where is the particle. So the mesh issues or the meshing issue is resolved. Now the second question is to reconstruct the contact pair that are actually necessary for contact mechanics problem and apply the right constitutive law. The constitutive law that we actually implement is very simple and very classic. So Gn is the normal gap functions, and Gt is the tangential gap functions. What we actually want to do is that we want to apply the Moore-Coulomb criteria to limit the tangential attractions as a functions of the frictional coefficients and the normal attractions. And the normal attractions in contact should be negative, which indicates in complex, it is in contact, or it could be actually be separate from the mechanics body. And with this constitutive law, we can simulate the problem, but the only problem is that we need to actually identify the gap functions that give us the relative displacement between particle, these two particles, maybe we'll call it 1 and 2. Okay, so the constraint that we have here is actually the Thun-Drucker conditions, and then the energy functional we use is actually contain multiple parts. It contains the penalty energy to prevent the interpenetrations, and the two energy functional that actually replicate the normal and the tangential response of the material. Now, the first thing that the first trick we're trying to do is to recognizing that unlike the extended finite element treatment, here we're actually using the indicator function to represent the boundary. As a result, we have the displacement field, but that displacement field would generate the strength in the background mesh for the bug. But what we actually need to do is also using that indicator functions to have a partitions of the behavior where we know that in the contact area, we use the contact mechanics and the gap functions to detect our stress response or the traction response, and then in the bug, we would actually using a classical finite element bug elasticity material to model the bug stress field. So here, without the regularizations, we would have the strong discontinuity that is actually very classic. We would actually detect the contact and then actually compute the relative tractions from the tangential elasticity, or actually from the frictional coefficient response. Here in the regularized with discontinuity, we will actually introduce the following KT behavior. We try to say that all the admissible tractions field in the tangential and normal directions are actually within the Moore-Coulomb envelope. And we want to impose the classical positivity, but now apply it into the interface displacement field. That the gap function change is actually related, actually proportional to the directions of the gap function change. Okay, so this is tangential directions, and we want to actually make sure that the yielding functions and the passing multiplier in the tangential directions are actually fulfilling the consistent behavior. Now, in order to prevent the interpenetration behavior, we would actually avoid using the extra degree of freedom to prevent the interpenetrations. Instead, we were just using a simple penalty method, which actually penalize the interpenetrations of the gap functions. So what actually happened is that the tractions would be actually generated whenever there is a slight overlap of the material. Now here, this is actually happening not necessarily when the material is overlapped, but when the indication functions indicate that there are potential contact in the material that we will describe in a moment. So right now, this part is actually really applied not necessarily just to the volume mesh or the voxel mesh contact mechanics, but also just applied to the general mechanics problem that prevent the interpenetrations. The new part, however, that are actually necessary and important is how to find these gap functions on the normal and tangential direction when we actually have an indicator function to tell us the location of the level set for the particle. So here we will use the level set to define individual particle. This method has been used from a previous work here, but also have been used by the granular element method that are developed by the Caltech group that are led by Professor Andrade. The major difference between this work and our work is that our goal is also to recover the stress field that are not necessarily available in the classical granular element methods. So here I'm just give a recap of what is actually a level set. A level set is a scalar functions in the spatial domain, and it indicates that when the level set is actually equal to 0 at that particular point, then we know this is the interface, okay? And we can actually introduce a sign there. If so, the sign can indicate whether it's in phase 1 or phase 2. So in this particular example, the interior is negative, the exterior is positive, but you can also feel free to switch the sign. But the sign change indicate that you are from the one point to another point, indicating that these 2 points are in different material or in different material state. So level set is also called indicator functions. So shown here is another applications which we will also talk a little bit about for recovering the middle axis for the void space. So here the level set is used to actually evolve the boundary. So we solve the level set problem by actually imposing the boundary values of the phase 3 equal to 0 to move, and that would be equivalent to imposing a displacement. This is one example of a rigid body motions. If you want to impose a rigid body motions, what we actually need to do is to evolve the level set of the values at the boundary and go through a process called velocity extensions that allow us to extend the known boundary movement into the entire level set, so we can actually allow us to represent the movement of the individual displacement. Okay, so sometimes this could be mixed by a mark particle method in which we can actually mark individual particle at the boundary and keep track of how does it move and converge the speed functions at the boundary and or the velocity in the boundary, and then we can actually solve the revolutions problem of the level set to update the geometry of the individual particle in each time step. This method is actually, the level set is solved in a voxel basis. In fact, in the finite volume regimes that are actually that are available on the internet. What we actually do is to couple this finite volume code with a homegrown material point level set code so that we can actually capture the movement and the deformation of the particle by generating the corresponding level set that represent the new boundary or the geometry information of the particle. Now, in order to detect the contact, what we actually introduce is an unbiased contact reference. This is in sharp contrast with the master-slave contact, where we actually define a master interface and then check the relative displacement of the other snake nodes in order to generate the relative displacement. Here we actually want to create something that are unbiased. There is no distinctions between master-slave interface, but we have an unbiased reference point. that are in between of two particles, 1 and 2, and tell us where is the reference. And from the reference point, we can compute the relative displacement by checking the revolutions of that the relative displacement of a point set on the boundary relative to that reference point. So to do that, we need the following. We have two level set functions indicate whether this is particle 1 or particle 2. For example, I call it I and j. Okay, so at this point, the level set for I would be actually equal to 0. These are scalar functions. And then for the level set j, so this is equal to 0 at the boundary. And what we're actually trying to do is to compute the minimum between the two. So what it means is that if you have a field, the minimum is actually compared point by point. So if you have a level set that looks like this for the first level set, and then for the next one you have this, then you take the minimum between the two, which means that this would be the minimum. Okay. Now, this minimum point can be reinitialized to actually generate this particular intrinsic shape. Okay, so this is actually useful because for two particles, we can actually using the shift functions to find out where is the rough location of the contact. And then we can actually find out which point set in the material, in the mesh that fulfilling this potential contact area. And from that contact area, what we want to do is that using these two interfaces to introduce a reference surface. Okay, so this is the active level set. And that are actually coming from the two. And what we actually can do from that, from actually finding the level set and then the contact area is to locate this reference point. This reference point for each individual particle would actually tell us where is the relative displacement. As we're changing the displacement field, what we actually need to do is actually for each incremental step, what we actually need to do is actually to project this contact point into the upper and lower surface, I and j. And then from the relative displacement of I and j, we can find out the gap vector. The gap vector will actually give us the normal gap and the tangential gap by actually checking from that reference point, what is the relative positions of these two particles moving. So we can match for each individual point, we can map it into, at the reference point, we can map it into the corresponding upper and lower interface. And if we can have a point by point pair, we can generate the relative displacement jump between the two particles. And from the displacement jump, we can recover the checksums from the corresponding Coulomb envelope constituted law. So the problem, once we define that gap function, the rest of the problem is really trivial. If we sample a very common contact problem with the energy functional for the normal and tangential contact and also the penalty, this energy would be added into the classical boundary value problem that gives us the first variations. And from that, we can get the width form, just like the displacement-based finite element with just the additional term for us to calibrate or to actually keep track of the contact. Now, the next ingredient that could be really helpful is the introduction of the material point. For us to capture the revolutions of the contact, okay, or in particular to help us carry out the important task of recovering the stress field that require a lot of refinement. So I think there are previous speaker that talk about the material point. So here we are mainly a user of the material point for this particular problem. So in all the problem, you can actually consider the fact that we have a continuum and then we partition it using a grid-like system. And we actually assign the material point to represent the mass or carry out a path-dependent material in that material point data. So we create a point set to carry out the informations, and from the material point, we will actually subject that material point to the background mesh. The background mesh can be solved in the finite elements, and then with the classical, maybe linear low-order basis functions. But the integration point can be just the material point or some kind of projections of the material point. And we actually can, if the boundary is conformal to the mesh, we can simply apply the boundary at the grid, or if it's not, we can try to project it back into the closest grid and then apply the and then interpolate or extrapolate the boundary conditions. In each time step, the external force would actually causing the background mesh to move, but instead of moving the background mesh, we would apply the corresponding displacement field in that material point. So the material point would move according to the displacement, like from what happened in the old material point to the new material point, and this movement would actually allow us to carry the informations into the evolved geometry. We then using a new mesh, and at the new mesh, we actually update the level set to give us the new boundary, and so that we can evolve the deformations without actually modify anything on the mesh. So now coupling the level set and material point will allow us to to capture the revolution of the boundary. But here is the one problem. In general, you don't know how many material points you would have for a given grid. So sometimes you can have 10 here, and sometimes you have 1 here, sometimes you have 2 here. And that can actually lead to some issues, like it will reduce the accuracy of the volumetric integration if you don't have enough integration point, or when you have too many, you may actually experience locking, particularly if the material is really incompatible. So what we actually do is the following. We use the trick that are very common in material point community. In each time step, we use in the initial time step, we will use the classical gaseous point locations, or maybe if you have a triangle element, we just put the material point at the middle to better capture the boundary. But at each point, when the material point is actually moving, we would actually trying to using the new material point value and using the moving least square projections to compute the corresponding values of any material property or internal variable back into the old gaseous point. The advantage of using the gaseous point is that you can control the accuracy of the integration mechanism. So integrations, numerical integrations, and for example, for 4-point or for chord element, you can actually control the order of accuracy easily by projecting the material point information back into the standard gaseous point locations. The drawback is that the moving these square projections from the new gaseous point data back into the gaseous point may actually introduce some error that kill off the accuracy. So you get some, you actually also lose some from that projections. But then the important part is that we don't want to deal with simulations where if the material point is actually have certain populations, you get a different quality or heterogeneous quality of volumetric integrations. So this is actually one of the tricks that can actually help the problem at the expense of some accuracy. So before we actually try to simulate the actual granular mechanics, we actually simulate some verification problem and compare it with the literature. So this is actually the first problem with a verification of 2 blocks that are actually prescribed a velocity, or actually in that case displacement, and then there's the tractions on the side And when the material heat, we want to see whether we can actually recover the results that are available in the literature. And so here is actually the results, and we actually found that the new method seems to work in that contact problem. And then you can see that the deformed shape is actually very reasonable. And the fact that these 2 points is not contact is because of these attractions. Okay, so we want to see, okay, if actually whether this pattern is actually corresponding or actually identical to each other. In the second example, we have an existing contact that doesn't necessarily evolve that much, and we want to check the slipping and then the stick. We want to actually see what happens when we apply the vertical stress or displacement, but not necessarily lead to the. We want to detect whether it's actually stick at the right moment and then start to slide once it hit the friction angle coefficients attractions. So you can see here. So in the first case, you have a continuous displacement field that indicating that the material is actually in a stick contact behavior. So the normal stress is actually enough to prevent it from slipping. But then later on, the horizontal displacement did show the relative motions. This is actually another classical verification problem. Another verification problem we also choose is actually also a problem that are also very classical. We apply the relative displacement and on the top, and then we actually fix the bottom, and then we see whether we recover the stress field that have an analytical solution available. The analytical solution is actually in the solid line, in a red line, dash red line, and the solid blue line, and then the point are actually the material volume calculations. As you can see, these simulations actually match pretty well for the contact MPM level set problem. And then we also check whether it preserves the symmetry. In this problem, we have the analytical solution of a spherical particle that have 4 perfect contact and in a periodic domain. And what we want to check is actually whether we can recover the stress field, the shear field in the XY direction, whether we can recover the analytical periodic pattern. And here we can see that the result is actually looks very promising. But one actually very important thing we want to also check is also the issue of mesh sensitivity. If you look at the history of the modeling deformable particle, there are early work that advocate using the discrete element and coupled with finite element. And the finite element would actually have a mesh by what we've shown here, perhaps a very coarse mesh. And then they have some contact that are determined by the discrete element. What they actually find out is that the result between the finite element DEM, the DEM that have a finite element inside for each individual particle is not so much different than the classical DEM. The reason is actually the following. As we investigate the problem, okay, if you don't have a fine mesh, you're not likely to capture the stress concentrations like what we've shown here. The reason is the following. When we have a small contact, okay, and this point, let's say that we have a point-wise contact, then no matter how small the force it is, force divided by area that approaching 0 will give us infinite stress. It will become a singular point. However, if you actually have a mesh, like what I show here, your integrations of the vertical stress is actually based on the gaseous point stress. And as the gaseous point is actually quite far away or have some distance from the singular point, the stress here is actually finite. However, what actually happened is that and hence the external force you actually compute from the mesh would also be finite. The issue, however, is that the contact would have a very severe mesh dependency, because as you refine the contact, you would have gaseous point that are much closer to the singular point, and the stress would just skyrocket. So to actually capture this problem without the mesh dependency, even in the small scale, we may need a size-dependent behavior damage model to help us overcome the mesh dependency, or at the very least, we need to have inter-rate dependency to regulate the damage, the singular point plastic deformations. But here we just want to show, okay, a small change on the mesh can actually increase the stress, and then that won't stop. Okay, because the finer the mesh you are, the closer to the singular point, and that is actually one of the problems that in the previous work in the FEM DEM, we never actually see any major difference between the DEM and then the FEM DEM, simply because there is not enough mesh to capture the contact point in very small area. In general, you may not have a point-wise contact, but the small area contact will also lead to a huge sensitivity on the mesh that are near the boundary. Okay, as you can see in here, it probably doesn't matter how coarse the mesh is unless it's super coarse. But you can see that the mesh quality or the number of gaseous point or the stress point, there is a resolution issue that need to tackle before we can actually resolve the stress field properly. Okay, so this is actually one problem. Again, but however, the problem is that here we actually introduce the trick that we use is that for all the outer boundary, we simply using a smaller mesh so that we can actually, in case there's a stress concentration, at least at the boundary, we can capture the details. Okay, but there are other better technology that we may consider, like the edge refinement or with the material point, or actually adding more material point to add the stress calculations more accurate, etc., etc. Now, but here we still want to emphasizing that the method is able to capture the different nature of the contact, and also for the single, for two particle, you can actually capture the multiple contact point that may not be otherwise necessarily available in the DEM simulations. So this is one of the simulation example. You can see the difference between a hydrostatic test, a pure shear test, and simple shear test, and how does the granular nature affect the microscopic behavior. In the isocompaction test, basically you actually make the sample a little bit smaller or a little bit bigger, but provided the contact is actually in there, it doesn't change that much. You can see that the contact that the profile are actually simply increasing the magnitude, but unless you actually have a very large, unless you actually continue to compact in it, you can probably see similar response without that much change. Now here, if you look at the second problem, okay, you see a little bit of difference. And actually, as you can see in these regions, or in these regions. So these detail can actually be only captured if we can recover the stress field and actually allow using a level set to. So I want to mention the following future work. In the future, what we want to analyze is not only understand the relationship between the force train that are obtained from the DEM to the finite element, but also how does that more detailed simulations may enable us to discover other topological information that are not available in the literature right now. For example, if I have the invariance of the stress, I can actually assemble different types of chain that are invariant chain for the first, second, third invariance, and then they may have different topology that can be supplement the force train or actually provide us more indicator of how to compute the stress in the homogenized granular ensemble as a whole, and also help us to have a new descriptor or machinery to understand the granular nature of the material. So this is the end of the part 2 of the talk. I want to thank the sponsor, particularly in the US, the Department of Energy, the Department of Defense, Columbia University, in particular the Army and Air Force that provide me the funding, and also the NSF including the NSF Career Award that actually propelled the whole research. I also want to thank particularly my former postdoc again, Chanchi Liu, for completing this research. This is actually the work that more or less done by him during a very short tenure at Columbia. So, I also want to once again thank the organizer for inviting me. And I want to thank the audience for have the patience to listen to my lecture in a virtual environment for such a long time. Thank you very much. And if you have any questions, feel free to send me an email. My email is actually wsun@columbia.edu. You can also look at the website here. Thank you. Thank you very much. And I hope we will see each other soon. Bye.